Hey, welcome everyone. Thanks for coming to this seminar. It is great chance that we have Yang Guo from Arctech Solar today to give us the talk. Yang is the global product market manager of Arctech Solar. He's now responsible for the forming systematic product strategies and leveraging Arctech Solar's tracking solutions. Yang is also UNSW alumnus with double master degree in PV engineering and innovation technology management. He's also entitled with distributed energy planner, ECE Reddit designer, and solar tracker specialist. He has more than 10 years experience in solar PV industry, contributing to over 600 utility scale and C&I project. With his expertise in engineering and finance. His talk today with topic is increased PV energy yield with superior Stow parameters enabled by rigid trackers. Now it's over to you, Yang. Thanks for your time today.
Yeah, thank you so much, Kevin. Thanks for the introduction, and thank you for everyone who spent this your valuable time at this I call like a sort of lunch and learn. Yeah, you can eat, drink, whatever you're comfortable. Yeah, I also prepared my wafer and tea here. So yeah, let's get started. Hopefully you will enjoy this presentation. So this presentation is mainly about solar tracker and also our Arctech white paper this year, which is focusing on the Stow parameters. Maybe many of you don't know what is the Stow parameters, so maybe we can kick a start from that from here now. So first thing, there's like a little practice. If I do this presentation like face-to-face physically, I might probably invite one of you to do a practice here to draw a solar tracker by yourself. I'll do this practice. I'll do it here for you. So I believe in many people's mind, a solar tracker would have a motor in the middle, right? There's like a little motor, maybe with drive or anything. And there will be like a long torque tube like this. And you hang your panels on it, like solar panels, 1, 2, 3. And there's like a full row of panels, another row of panels at the two like wings of a tracker. That would be a solar trackers that you normally see. And there are some like posts, a motor post like this. Okay. And sometimes you might see some springs or bracing here, just try to absorb the vibration. But anyhow, this could be the solar tracker you've seen in many projects. And here I give a better looking one. So like I said, one motor in the middle. It could be a push rod, could be actuator, whatever it is. But the main moving parts will start from here, and the both end will be the free end, like the wing of the birds. But if that's the tracker in your mind, that would be the solar tracker like before 2020. Yeah, after 2020, solar tracker has like a sort of like a renovation. So let's quickly recap the solar tracker technology evolution. So before 2010, there are multiple early technologies, and I believe you guys are from SPRI. You know that the dual axis tracker, a tracker can both tracking east west or north south, could get the most PV energy, right? But if we look at the LCOE, it's not always the best option. And I would say in most of the cases, it would be quite expensive because this type of tracker costs a lot per watt. So in the 2010s, some tracker manufacturers, they find the right way. They do single axis tracker. So only tracking east-west, but that will largely simplify the structure and also bring down the cost. Yeah, although it does not produce as much energy as the dual axis tracker, but if we look at the LCOE, it becomes a pretty good option. And by the time link row tracking system, which was led by Array Technology, an American company, was dominating the market. A link row technology is like there are like several PV rows like this, and they all linked by one very long big push rod, and there is a motor to push that rod and will control a multiple row of trackers. And then there is like another advanced technology. It's called a single row single axis tracker. So it's like what I've presented here. So it's like a one row per motor, one motor per row. So this little motor can control just one row, but this motor is small, and you will have like a more flexibility in the layout or in the undulated land. This is also single axis. But like I said, this has been out of date. These days, we are looking at the multi-drive point trackers. So the difference for this one is there's not just one motor, or we call the drive points, but we also have other drive points, and they are linked with a transmission shaft. I'll show the detail later, but here you can have a very quick look at the difference. So the original design, the single point drive, comes with a flexible structure, and the new design will have a rigid structure. Let's look at the details and the backgrounds. This is the background. So if you're familiar with the evolution of PV module, you can see that in the past just 2 to 3 years, solar modules, PV modules are becoming like larger and larger. So before 2019, we are looking at the panel format normally like 2 meter by 1 meter. Yeah, and that has been there for 4 to 5 years. But suddenly things has changed. Yeah, it just suddenly evolved from the 400 watt to 500 watt plus, 600 watt plus. And these days, PV module has become so big, because I believe you all know that the cell efficiency hasn't changed that much. So the only way to increase the wattage per module is to increase the size. So today we have 182 millimeter PV cell and the 210 millimeter PV cell. These are the two major commercialized PV cell for the PV module. And the size for this one can go up to 2.4 meter times 1.1 meter, and this one is about 2.4 meter times 1.3 meter. They are like very big. And what does the large module impact on tracker? So you can see very obviously it will make a solar tracker much wider because you have like a bigger module, and also longer and wider, right? And large module size can make the tracker more fragile. It can easily get deflated and make the entire tracker unstable. And in order to study these effects, normally a tracker manufacturer will need to do the wind tunnel test. And luckily here we have done our protocol in the CPP wind engineering facility. This is a wind tunnel in Sydney. So these are like our little model. So you can see this big plate. So what they do is there will be a wing coming from one direction, and they can do the test, like a group of little trackers in there, and they would do the test in each angle. Every time they can rotate these big plates a little bit, like every, say, for example, 5 degrees or 10 degrees, and understand the behavior of the design. And for this wind tunnel test, we normally collect those design coefficients and understand tracker behaviors. And with those coefficients, we can design specifically for different solar projects. And here we have a chart, a conceptual chart for a test result. So in this chart, you can see that the x-axis represent the different test angle, like this. We test at a different angle, and the y-axis, the vertical axis, represent the wind speed in the wind tunnel, and each dot represent a single test. Let's take this one for example. What does this dot mean? It means in this test, I placed my little tracker into the wind tunnel. This is like a 40, maybe 44 degree. Let's say 44 degree. So I do a 44 degree. This is a positive 44. So the wind comes from this direction. So it's like a nose up. This is your nose up 44 degree. And I place the tracker into this wind tunnel. And then let's increase the wind speed in the wind tunnel. And as the wind speed increase to this level, this model gets so deflated. The deflation is over 32 degrees. So in that case, we believe the actual tracker cannot survive in the real environment. So if that's the case, the real tracker can get damaged. So this is the point that where the tracker get damaged at this wind speed with this tilt angle. And then we do several tests under maybe different orientation, different wind speed. So we got many of these dots. And for all these dots, we found that they are all above this dark curve. So which means these the tracker is okay, will be safe under this dark curve, right? And if you want a solar tracker to rotate like freely, to track freely without any problem, it can only be the lowest point, somewhere below this lowest point. This dark curve is called the critical wind speed. Yeah, and we found we will set like this dashed line. It could be slightly below this lowest point. We set it as the wind stow speed. So which means the environment wind speed, if the environment wind speed is below this dashed line, the tracker can operate like normally, no interference, everything's good, functioning well. But if the wind speed goes beyond this dashed line, the wind stow speed, the solar tracker will have to go to a stow position. And the stow position for a solar tracker is somewhere right here. So this is a nose down towards the wing, in between, well, it could be 15 degree, minus 15 degree, or it could be even minus 60 degree. But it will have to be a nose down because at that position, you will have the highest critical wind speed. Let's say, for example, it could be maybe 40 meters per second. Yeah, for example. And this, let's say 60 meters per second, okay? This is the wind stow speed. And this is the chart for a traditional solar tracker with one motor, one drive in the middle. Okay, let's see what happened if we use a large format solar panels. If the solar panel is big, That makes the tracker long, wide, tall. It will drag down this critical wing speed line. It'll be like this. So that squeeze the operational range. Yeah, it used to be 60 meters per second. Now it become 12 meters per second. Yeah, and you still need to stow at a steep stow angles to get like high critical wing speed to cope with the extremely like a high wing speed. So that's an issue, right? And also there are some other issue on the solar panels, because with a large format PV module, it can easily get, okay, I'll just use this wafer. It can easily get swaying. Yeah, we call it the glapping instability, or because it's big, it can easily get cracked. So that will cost these potential risk, especially for solar panels. If it's not cracked, you might also get like a micro cracks within the cell. So these unpredictable risks are increased. But what if multi-tracker? This is a curve for a multi-drive tracker. This is the curve for the multi-drive tracker. The previous one was from a traditional drive, right? Traditional single point drive tracker. So for multi-point drive tracker, we flip up. So the curve used to be like this. You can see here. We flip up to this. It's like a reversed V shape. So in this case, you will find that the lowest point become somewhere here. Yeah, it was like 16 meters per second or 12 meters per second. Now it can become like 18 meters per second. We actually increase the critical wing speed everywhere. Yeah, and the wing stow speed, we can set it much higher. And also we can safely stow the tracker at 0 degree or somewhere nearby. Horizontal stow position as written here. So that will help to increase the tracker's like strength. The tracker will be able to cope with a much higher wing speed. For example, this could be, let's say, 70 meters per second, much higher than here. And what else? If the tracker is like stowing on a horizontal stow position, the wing can just easily pass through the top or the bottom of the panel, and the wing pressure onto the solar panel will be significantly reduced, right? Okay, so for our design, Arctech, we are like the kind of the pioneer of the multi-drive trackers. In late 2019, we launched the SkySmart 2. It's a 2P tracker, and later last year we introduced the Skyline 2. It's the 1P multi-drive tracker. I'll just give you a little briefing here. 2P means a 2P tracker means 2 rows of panels, and they are in portrait. Row 1, row 2, and 1P is like a 1 row. Okay, that's 1P. And both trackers will have more than 1 driving points. So the motor is right here for SkySmart 2, and we have a transmission rod. You can see that to link them together. And for the 1P, the motor is right here, and use the transmission rod to pass the driving force to some other driving points. And this can be decked up. You can make another piece here and another piece there. Yeah, you can easily make it longer. That's no problem. So that's how we design our tracker and make it more make it stiffer. And for the Skyline 2, we can easily do a 22 meters per second stow wing speed, and a SkySmart 2, that's 20 meters per second. Here I can also quickly show you a 3D model that will make you that's much clearer. So here is the motor, and that's the gearbox, and it rotates. The motor will rotate the transmission shaft, and also will take the torque tube like rotating. And with this transmission shaft, you can see that it will link to another drive points. So altogether, for this model, there are like three drive points. Here's the other one. All right. All right. For the past, everything I've just talked about can be simply concluded in these logic chain. Yeah. So as you can see that with many fixed points or drive points, we can have a more rigid tracker. And with this rigid tracker, we can have like a smaller pressures onto the panels or the components, so we can make lighter components and make some saving on the steels. And here I would like to introduce another part. This part will be the main focus on the white paper. It will tell you why this kind of structure can help you to increase the energy yield. So we made a case study in our white paper. So this case study is a virtual 100 megawatt solar farm in Texas, USA. So here we compared 5 different solar trackers. Skyline 2, Sky Smart, they stow at 0 degree. And the wind speed threshold or the wind stow speed is 22 meters and 20 meters per second for them. And we also compared 3 traditional solar trackers. They were still at 30 degree or 45 degrees. And with the wind speed threshold of 16, 14, or even just 12. And on the right-hand side, they are representing different type of trackers. And let's have a look at the wind speed distribution in that area. So this is the histogram of the wind speed. And please keep in mind that this is an hourly wind speed. And when we talk about the wind speed threshold, we are talking about the 3-second gust. So it's not, how to say, it's not like the same kind of a unit. So normally we would need to use, a dust curve to transform the 3-second gust into the hourly average wind speed. The knowledge behind it might be a little bit complicated, but let's just make it simple for now. So you know that if you need to measure or need to compare the different wind speed, you might need to use the dust curve to do this transformation. I mean the the measurement intervals. Okay, so now we will use these to do the comparison, and then we replaced these wind speed into the histogram. Then you can see that Skyline 2 is right somewhere right here, and the tracker C is right here, which means during these hours, the tracker C, like the wind speed has go over the tracker C's stow wind speed. The wind stow speed, sorry, and these hours account for almost 15% of the annual, like all the hours of the year. Yeah. And for Skyline 2, only like 15 hours right here, and that accounts for just 0.17%. And what does that mean? Let's take a 1-day profile to further explain this. So here we picked the 17th of June. This is the 2020 data, the historical data, and we picked this 7th of June to do this example. because for this particular day, we have some high wind situation, but also it's a very sunny day. Yeah, so let's look at this curve. Yeah, you can see that the orange one, it's the fixed horizontal tilt. It's energy output from a fixed horizontal tilt. So it looks like a bell shape. And the blue one represent a solar tracker energy output. Yeah, it's like fatter because the solar panel is always facing the sun. Yeah, and in the middle of the day, like lunchtime, like now, it matches the horizontal, right? Yeah, and then it creates more energy in the afternoon. The green one represents a panel fixing 30° towards the east, and the yellow one is the 30° towards the west. It's like two fixed tilt. And the bar behind, the gray bar behind, represent the wind speed of that day. So later on, I will replace some of the blue line with the other colors under different conditions. So let's look at the skyline. So it's a solar tracker with a 22 meters per second wind stow speed, and also it would stow at 0°. And this dashed line is the wind stow speed here. And as you can see that the gray bar, it has never touched that dashed line. So the energy output from the skyline 2 will be perfectly match the uninterrupted tracking. So they are the same because nothing has interrupted the tracking function. And it's similar for SkySmart 2, although it has like slightly lower stowing speed, but it doesn't got any effect from the wind speed. But things has changed a little bit for Model A, the Tracker A, because it has a comparatively lower wind stow speed. So after 3 p.m., the wind speed has gone over this critical wind speed. Sorry, the wind stow speed. So the tracker will have to go to a stow position like this towards the wind. And luckily, this is a western wind. So sorry, what I forgot to tell is that let's come back to this line. Sorry. So this is western wind, and this is west, but this is east. So you will see the difference later. Okay. Okay. Let's back to here because it's the western wind. So from this point, the tracker goes to a fix. So it's like it used to follow the blue curve, and then and this particular points, it follows the yellow curve because it's stuck there. It stows at the 45° stow position. Oh, sorry, 30° stow position. Yeah, and the shaded area, this little piece, will be like the energy lost or the energy that this tracker cannot captured during this time. Let's look at Model B. So the case for Model B will be a little bit worse, like I just mentioned, because for this time it's like the eastern wind. So the tracker has to stow towards the east, like this. But while the sun is right here, right? So the energy loss is bigger. There's like a little gap here, a big gap here. So it will cause like more energy lost in after like somewhere between 2 p.m. and 3 p.m. And the worst scenario is for Model C, the Tracker C, which would do a 45° stow position. But you can see that the energy loss here will be kind of minor because it faces the sun maybe better in the afternoon while doing the west-facing stow position. And you can see there are a couple of energy loss in the morning. All right, this is our one-day analysis, and if we conclude 365 days or 8,760 hours data, we come up with these this conclusion. You can see that inevitably there will be some energy losses for multi-drive trackers, but it's kind of minor. It's like somewhere around 0.1%. But for other type of trackers, like the traditional type of trackers, these will become a different scale. It will be like around 1% or even up to 4%. If we translate that into energy losses, there will be some gigawatts of losses. And if each megawatt hour is worth 28 US dollar, it will become like this much revenue lost per year. We can make these figures more accurate if we do this analysis with half-hourly wind speed or 15 minutes wind speed, 10 minutes, 5 minutes. That's not a problem. But what you need to take away is it will definitely follow this trend, no matter that's like a 1 hour data or 5 minutes data. This trend is for sure. So it's always like that. With a higher wind stow speed, there will be less like energy losses, and with low wind stow speed, the energy loss will be huge. And in this particular case, we found that 0 degree will always perform the best, better than 15, 30, and 45. You see, steeper the angle, the worst energy output it will get. But what I like to mention that this is not always true for this particular, let's say, phenomenon, because in some cases, a steeper angle might do better than 0 degree. That's because energy losses is a kind of occasional events, and if the high wind situation happen to be in the early morning or late afternoon, and sometimes these steeper angle might perform better than 0 degree. Let's look at some economy analysis. I know most of our SPRI students would focus more on the optimum engineering solutions, but in the real world, in the industry, we always look at the dollars. So let's just create these two simple finance models. So project A and project B are actually the same project, same 100 megawatt project at the same Texas location. What's the difference is that project A uses a multi-drive tracker, and project B use the model B here, this one. Okay. So let's just assume all the inputs are the same. 100 megawatts initial cost points like 70 cents US cents per watt. But the difference comes from the energy yield, because model B will have the wind-induced energy losses. It will have approximately 3.5 gigawatt hour energy losses per year. And at the end of the day, if we're looking at a 35-year project lifetime, it will accumulate it to $3.1 million lost, and 0.17% IRR decrease. IRR represent internal rate of return. If you don't know what it is, probably you can do some Google. Yeah, it will represent the kind of like financial benefits or strength of the solar projects. Yeah, maybe sometimes later we can have another course to another presentation to explain about the solar farm IRR or NPV or any other stuff. Yeah, and we all have NPV here. So if we use the 6% discount rate, the NPV difference will be 1.3 million. Just give you a very simple explanation. This 1.3 million means you will have, so this 3 million loss is equivalent to 1.3 million loss in day one. So it's like if you decide to invest this projects in day one with Model B, you are like deemed to have 1.3 million loss immediately. Okay, let's just assume that project B has done some had done some like upgrades here by reducing the cost. If they can't change the model, okay, they reduce the cost by like this much, 1.3 cents per watt. To do what? They are trying to match the IRR. They want to make the IRR equal. So they reduce their price by this much. So which means a Skyline 2 can help the project save this much like investment at day one, or create this much value at day one. And even if the project B owner decide to go with this decision, they are still facing some difficulties. First is how to close this gap and how to close this gap. The only way is to increase the magnitude of the investment. Rather doing 100 megawatts, they might need to do 103 megawatts, and then have to require more lands, have to do like the redesign, and there will be many other headaches coming through. Okay. And in our white paper, we also show some results from some other locations, and you will see that the difference might not always the same between, well, it's always different between different sites. Let's take somewhere near Sydney, for example. The worst scenario can't go over 1%, but in Europe, in Madrid, it's somewhere over, the worst scenario somewhere over 2%. And if we look at China, northwestern China, yeah, they also have some strong wind, like high wind speed situation there. So the gap is also kind of big. And this is Middle East, Mecca, you can see that it's even a bigger difference there. And like I said, there are some anomalies. In this particular case, 0 degree is still good. This is Chile. 0 degree is still good, but 45 degrees is not the worst. It's better than 30 and 15. Yeah, and in some cases, like I said, the 0 degree can even be worse than the others. Okay, that's almost everything about the presentation. Here, I would like to quickly introduce a little bit about our company and our training center, our position in Australia, etc. So first, we have established a training center somewhere near Melbourne. So right there, we have 3 solar trackers, a 1P and a 2P trackers. They are the older model, but they are fully installed with solar panels, and they are functioning well, and we are doing some tests on those trackers. So those trackers will have monofacial and bifacials. So we have 4 groups to compare: 1P versus 2P, monofacial, bifacial, for different combination. And we have this Sky Smart 2. It's a multi-drive tracker, but it's a skeleton. We don't have panels on it. So this tracker will be there for training purpose. So with this tracker, you will see the actual structure of the of a solar tracker, and also, if possible, some trainees would like to do hands-on installation practice. Yeah. So I would like to use this opportunity to propose some cooperation with SPRI. We can do summer camp, or to invite professors come and have a look, do some study testing, whatever you like. But I believe this will be a good facility there, and everybody can use it for some good purpose. And here, this is a snapshot of our company. So Arctech is one of the top solar racking companies, and we enter this tracking business from 2014. And right now we are ranking as the #4 solar tracker manufacturer in the world, and also the #1 in Asian Pacific region. And in Australia, we have I think now it's more than 600 megawatt solar farm deployment across the nation. Okay, that's all. That's everything that I want to present for this section. Thank you.
Okay, thank you, Yang, for your great talk. A lot of new knowledge for me, at least.
You're welcome.
Thanks. Do we have any question in the audience for Yang? I didn't see question, but actually I have like a couple of questions.
Yes,
you talked about the trackers, but I don't know if SPRI people we are doing research on this, but during your like distribution of the solar farm in your like field research, what kind of module design you think is the most important points for you to like match with your trackers? Did you like have like specific requirement of the modules, the silicon modules you think is like have better matching with your trackers when you design?
Okay. Yeah, thanks for that questions. To be honest, in reality, in the industry, it's not the module to fit trackers, but it's another way around. It's the tracker to fit modules. The reason is, let's go back to the very first background here. So if we have the sense of the investment of the PV module, I mean the proportion of the module cost of the entire EPC cost, the module would be account for, let's say, maybe a quarter or 30%. But for solar trackers, it will be merely maybe somewhere around 10%. Yeah. So modules play a more important role. So module, they increase their size, they want to make them more advanced, and solar tracker in the most of cases will need to follow and adapt. Also, we can do some like prediction. For example, we might think in the future the module can go up to 2.5 meter times 1.5, whatever. It could be, or it could be not. And then solar trackers will have to give some redundance. Our design should have give some redundance to fit that trend. Yeah. So to just give you a very simple answer, we can fit all commercially used module in the market these days. So there's never a problem. And I can give you a few more other tips. So these days you can see that solar trackers are getting longer and longer. They're trying to make themselves longer to fit more modules. And for our trackers, our 1P tracker can do 130 meter. That's the max for now, max length for now. So if the module can fit that length, that would be the best. And also, and for the 2P tracker, the SkySmart 2, it can do 95 meter long. Yeah. So if your module, like the number of modules per string, 4-string or 6-string, whichever, can try to potentially fulfill that length, that will be potentially be the supreme design. Yeah.
Oh, okay. Thanks. And regarding the wind speed, I can see you designed them for like 2022 meter per second. Is the number related to the real like application scenario, or is the real wind speed is like around that number, or is your capability to design that like high like wind speed resistance of your tracker, or you have plan to increase this number in your future?
We don't know what. So first, the high critical wind speed, 18 meters per second, 20 meters per second, 22 meters per second, were only enabled by rigid trackers or the multi-drive trackers, multi-drive point trackers. And I don't know what kind of potential it can be, maybe in the future, 25 meters per second, or could be more. But like, yes, the simple answer is yes, the capability for example, the 1P tracker, we can do 22 meters per second. That's for sure. And in most of the cases, you don't need that much, because if we look at this like chart, it doesn't make like points to go even higher, because higher the wind stow speed means the higher the cost. If for example, let's put a 23 here, for example. If we can do 23, 24, yes, it could be possible, but you need to throw more steel, you need to invest more steel in the tracker, but it does not give you any extra benefits. So in most of cases, we are looking for the balance between the parameters and the actual environment. But just give you, so these presentations give you a conceptual understanding with, let's just simply say, with the same amount of steel, a multi-drive tracker can save or can maybe increase the critical wind speed compared with the traditional tracker. If you throw the same amount of money into these two types of technology, then you would definitely go with this, because this will help you to get, let's say, 1.6% more energy and save the panel.
Okay, yes. Actually, that's my question. If you like increase the wind speed, will you like increase the cost? Actually, from your answer, I can see it will not increase the cost, but just increase the quality of the tracker. Right?
Yes.
Okay. Yeah, that's great.
Yep.
Do you have other questions from the audience to ask Yang? I didn't see.
Yeah, can I ask a question?
Yeah, sure. Zibo.
Hi. Thanks for the great presentation. Yeah, this is Zibo. So
You're welcome.
I have a few questions. So in terms of corrosion protections, are you guys using just galvanized steel or using some fancy alloy, like the one?
So when you do a real world projects, we always think about the cost balance. So you have first and foremost, you have to make sure that you meet all the requirement and standards. And second is to try to save the cost. Yes, the hot dip galvanized steel is the commonly used material for solar trackers. You could also use the aluminum alloy, but that will increase the cost a lot. And that kind of like material could be very light and sometimes can't hold solar panels. So not just us. If you look at all the solar tracker, I would say the top 10 solar tracker manufacturers are all used hot dipped, like the galvanized steel in the market. But I would say there could be some smaller manufacturers. They don't do very large scale projects. They might do, let's say, 4 trackers in a farm or next to a poultry. Yep, they might use some smaller, lighter material. but those cannot easily apply to a massive scale project. Hope that answers your question. Yeah.
Yep. And also, have you guys looked into active protections? Because I know some company have this solution which they had just inject the electron into the steel structure. So, so instead of oxidizing the steel, by injecting the current into the structure, that can extend the the life of the structure. Have you guys looked into that before?
Well, to be honest, I'm not the expert on the corrosion. I remember last year we, like myself, I also need to enter a webinar about the corrosion. But I think we have this type of expert in our headquarters. I think the best way is maybe we can talk about this after the presentation. I can maybe link you to our expert back in the HQ.
Yeah, great. That'd be great. Yeah, thanks.
Yep, no problem.
Okay, thank you. Do you have other questions? Otherwise, I think our time is also approaching. We need to close the presentation today. Yeah, nice to see your training center. You just showing us. I think if people in Spree want to do some research or just visit your center, I think people can contact Yang for this. I can see it's very nice. You have panels and trackers. If people want to do such research about the tracking system, you can contact Yang for more details. Yeah, thank you, Yang, for your time again. Thanks. And,
yeah, no problem. Hope you enjoy the presentation. And always let me know if you have if you are interested in visiting the training center. We can do a group visiting or a specific training or whatever. Yeah, I hope this could be a part of the contribution to Spree UNSW.
Yeah. Thanks. Okay. Thank you again.
All right, thank you, everybody. Bye.
Okay. Bye.